one way we can now, one thing we can do now, for example, we have calculated the average residual life and average age and so on. Now, we can actually calculate the distribution of the age. Okay. So, or distribution of residual life or whatever you want, right. Now, how would you do that? So, you would want to, so you want to look at, let us say the distribution of the residual life, you want to look at y of t less than or equal to some little y, that will be the distribution of. Now, you are looking at the fraction of time that this residual time is less than or equal to little y. What is the time average of such a reward is what you want, right. You can, so therefore, you can take a reward function which is equal to 1 when y of t is less than or equal to y and 0 when it is not the case, and you find the time average of this, you can use the renewal reward theorem to get this time average, right. So, this is a good example of so you want to take, let us say r of t is just indicator okay. Now, if I take the time average of this function, see y is some little y is something fixed, okay. I want the CDF, so to speak, of y t, right, little y is fixed. So, I am looking at the average fraction of time that y t is less than or equal to little y, if I find the time average of this reward function, right. Okay, if you want to write this as, if you want to write r of t in the form r tilde z t y t, right. So, this is equal to 1 when x t minus z t less than or equal to little y and 0 when x t minus z t is greater than y. I am writing it as r of z d comma x t, that is what we have chosen, right. So, just to give you a picture, let us say that is my, that 0, that is my renewal process, some particular realization of the renewal process, and little y is something fixed, okay. Little y you fix whatever you want. Now, my reward function r of t will be 1 whenever the residual life, the time to the next renewal is less than or equal to little y. So, at each time t, so my time is let us say here, I will say is my time to the next renewal less than or equal to y. If it is not, I will give 0 reward. At some point, let us say here it will start becoming 1, right, and the width of this will be how much? Little y, right. So, when I am here, when my time is here, my residual life becomes less than or equal to y, y is some, you fix a little y, right, then your reward will become 1, otherwise it will be 0, correct. Again it will become 0 here if it were the case that the next renewal interval is greater than y, right. Suppose, so this is x1, so the way I have drawn it, x1 is bigger than y, little y, that is why it was 0 here, and when the residual time became less than or equal to y, I got a reward of 1, and the way I have drawn it, this x2 I have drawn it to be smaller deliberately. So, if x2 were less than y, I will start accumulating a reward of 1 straight away, right, and then this renewal interval is much longer. So, my reward goes back to 0, right, again it will become 1. So, this will be y, right. So, if you look at now what is this equal to? This is simply what x 2. So, I have the way I have drawn it x 2 is less than y, right. So, in the picture x 1 is greater than y, x 2 is less than y, and x 3 is greater than y, and so on.
Sir, why is it going to 0 immediately after x2?
Because your reward becomes 0. See, at this time what is your residual time? X 3, but x 3 is bigger than, the way I have drawn it, x 3 is bigger than y. So, it becomes 0 immediately, and then it keeps at 0 until my residual time becomes less than or equal to y, then it shoots up to 1 again, alright. And the reason it did not fall down here is because I have drawn x 2 to be smaller than y. If x 2 were bigger than y, again it will fall down and pick up, correct. Yeah, clear. So, now I want the time average reward of, so want to calculate what? Limit time average fraction of the time that residual time is less than or equal to y, right. This is what I want, integral 0 to t indicator of y t less than or equal to y. I think I should write d tau, no, y tau d tau. And this is the reward function in question. Now, what is R n now? Now, question, what is R n here? Yeah, it will be the area under. So, this is R 1, right, this area is R 1, this area is R 2. This is the analog of the isosceles triangle areas, right, except the function now is different, right, and this guy will be R 3. So, R 1 is how much? Y, little y, R 2 is x 2, R 3 is y. So, what is R n? So, if your x n is larger than y, your R n is y, right, but if your x n is less than y, R n is x n. So, R n should be what? So, it should be y when x n is bigger than y and equal to x n when x n is less than or equal to y, correct. So, what is that R n? R n should be min or max? Min of x n comma little y, finished, right. So, thus by RRT, Renewal Reward Theorem, I have the answer already, right. Limit t tending to infinity 1 over t integral 0 to t indicator y tau less than or equal to little y d tau is almost surely equal to expected min x n y over x bar, okay. correct, because Rn is min x and y, xn comma y. So, expected Rn is, so this guy is just Rn, I have taken expected Rn, that is all. Okay. Now, what is expected min x and y? Now, expected min of x n comma y is simply integral 0 to infinity probability that comma y greater than x dx. Right? Why? Non-negative random variable, expected value is the integral of the complementary CDF, all right. So, this is clear. Now, this what does this boil down to? Yes. So, this is just, so if little x is less than y, sorry, so this will be, this will become like this, right, this will become integral 0 to y probability that because x has to be less than y, right, x cannot go from 0 to infinity because you are looking at the event that min of x comma y is less than x, greater than x. So, x cannot be, when x bigger than y the integrand becomes 0, correct. So, that is all remains when so when you have minimum of x comma y, where if you are looking at values of x which are less than y, then min of x comma y will simply be x n comma y will simply be x n, okay. That is that. So, if you want to draw, if you want me to draw a picture, you are looking at this random variable, right. So, let us say that, let us say this is my original CDF, okay. It starts off at 1, then decays down to 0. It does not have to be a nice continuous function like this, but we have drawn something, all right. Okay. So, this is the CCDF of x n, I want the CCDF of min of x n comma y, right. So, if you have, let us say y is here, okay. So, when x is less than y, all right, so what is the probability that min of x n comma y is greater than x? It will simply be probability that x n greater than x, correct, yeah. And when x is greater than or equal to y, what is the probability that min x n comma y is greater than x? 0, correct. So, the CCDF, let me draw this in a different color. So, the CCDF of probability of min of x n comma y greater than x, if I draw that guy, it will follow, too bad, how do I undo, yeah. So, it will just follow this curve and then drop down to 0, that is what I have integrated, correct. I am just justifying this step in this picture, all right. So, perfect. So, let us go back to this. So, we have limit t tend to infinity 1 over t, the time average fraction that my residual time is less than or equal to y is simply integral 0 to y probability x n greater than x dx over x bar. Okay. So, this you can think of as some sort of a CDF of yt, but it is not really a CDF because it is the time average fraction, right, which is why I put it inside quotes. It is the probable, it is at some level it is the time average fraction that yt is less than or equal to y. Since time averages are generally equal to ensemble averages, you can look at it as the expectation of this indicator, expectation of the indicator yt less than or equal to y. And what is the expectation of an indicator? Is the probability of that event, right, probability yt less than or equal to y. So, it is a little bit like saying if the renewal process is running for a long time, what is the CDF, what is the probability that your residual time is less than or equal to little y, it is this answer, integral 0 to y CCDF over x bar, okay, almost surely. Yeah. So, there is something quite nice about this, there are two remarks that I would like to make about this answer that we have obtained. See, the one is that even if x n this interrenewal times are not continuous random variables, they could be discrete or mixed or whatever, the CDF of the residual life is the integral of some nice function, right. So, we can actually speak of some sort of a density with the same understanding that it is not quite entirely rigorous, right, it has a density of that form, right. So, the density of the residual age is like the CCDF of your xn's. See, the xn's do not have to have a density, but the residual time always has a density, if you believe that this time averages and ensemble averages will be the same, okay. All right, because I am just differentiating what I have above, right. So, it is nice that even if you have a renewal process in which xn's are discrete or mixed or whatever crazy thing, the residual life will always be a sort of a continuous random variable asymptotically when t becomes large, all right. That is one thing. The other thing is that if you find the expectation of yt now, the average, so this is some distribution, do you get, what do you get? Now think about it. First of all, is this a valid density? It has to integrate to 1, right. If you integrate it from 0 to infinity, what happens? The integral of the numerator is, yes, x bar, denominator is also x bar. So, you get 1. So, in order to, if you want to calculate the expected value of this distribution, what will you do? You will integrate y times p x n greater than y 0 to infinity, and that will be like your second moment. You can calculate using integration by parts. You will get recover the answer for expected yt or average of yt, which is x n square, expected x square by 2 x bar, right. You will recover that from here, okay. So, this is very nice, right. So, we have the distribution of residual time, okay. Likewise, you can actually also calculate a similar calculation shows for the age, the same sort of an answer you will get. same argument. Okay. Homework, you can calculate the distribution of the duration x t. Okay. So, here you will take r of t equal to indicator x t less than or equal to some little x, same procedure. Second homework, calculate the joint distribution of x t and z t, or x t and y t for that matter, does not matter, right. For here what will you take? R of t equal to indicator, yes, x t less than or equal to x and z t less than or equal to z. This is the reward. Okay. You can calculate the entire joint distribution of these x's and z or y and z. Okay. So, once you get the joint distribution, you should be able to do sanity checks like can you recover the marginals, right. Please try this as a homework. Okay. It is an interesting exercise in renewal reward. Okay. So, I am done for today.